Here are the different terms we're going to look at today. So let's go ahead and begin. So we looked at a variety of two-dimensional figures. We looked at triangles, quadrilaterals, polygons, and circles. And so all these things we've looked at so far. Just a reminder that triangles are 3 sides and 3 angles. We have scalene triangles, right triangles, isosceles triangles, and equilateral triangles. We also looked at quadrilaterals, which are 4-sided figures. We looked at parallelograms, rectangles, squares, and trapezoids. Give me 1 second. Okay, then we looked at polygons. We were able to classify polygons by the number of sides they have. For example, a pentagon has 5 sides, a hexagon has 6 sides, etc. And then lastly, we looked at circles. Circles are basically a figure with no straight sides or vertices, but they do have a radius and measures. And so all these things we've worked through so far. And so now we're going to get into 3-dimensional figures. Okay, so a prism. So that's the first one we're going to look at. So what is a prism? A prism is a 3-dimensional solid whose bases are 2 parallel congruent polygon bases and whose other faces are parallelograms. So basically what it's saying is its bases are 2 parallel congruent polygon bases. So these would represent its bases. This top part and this bottom part, that would be its bases. So we can label that as its bases. Its faces, on the other hand, are going to be the parallelograms. And so these would be the faces. Here's another example of a face. So bases are going to be the top and the bottom part, and then the faces are going to be all those around it. So prisms can be created by stacking polygons to create the solid with repeated translations. And so here we see that prism being created, and it kind of looks like we're stacking those different polygons on top of each other. And as they continue to stack, they create a 3-dimensional figure. And so that is what a prism is. The polygon that is repeatedly stacked is the base of the prism. So as we continue to stack those things, once we get to the base will be equal to or look exactly like that polygon that we have stacked on top of it. And so in this one, we have stacked something that looks kind of like a rectangle or a square. And so that, let's say it's a rectangle. So basically we're stacking those rectangles on top to create that 3-dimensional figure. And because we're stacking rectangles, the bases will be rectangles. So that's kind of what this is saying. The names of the prisms come from the shape of the base. So we have a hexagonal pyramid. Basically what's happening here is we're stacking hexagons. And so therefore our bases are hexagons. Again, the bases are these top and bottom parts. Okay, an octagon, an octagonal prism, same thing. Basically, we're stacking these octagons on top of each other, these polygons on top of each other, and that gives us our hexagonal base. And so we name our prisms based on whatever their bases are. We also have pentagonal prism, same thing, this would be the base. The bases would be that pentagonal because the prism is named after the base. We have a rectangular prism, again, the bases are those rectangles. A triangular prism, the bases would be those triangles, and we're stacking those triangles on top of each other to get this 3-dimensional figure. And then lastly, a square prism. So once again, the prisms are named based on the shape that is shown at the base. Okay, any questions about prisms? Questions, concerns? No? And then just a little more about the vocabulary. So we have a lot of different bases. Bases can be anything like the bases, or we have lateral faces. The bases that we know are going to be the top and the bottom parts, and those tend to not look exactly like the lateral faces. The lateral faces tend to take another shape. And so in this example, for example, our bases are triangles, and then their lateral faces, which are going to be these faces right here, take a entirely different shape. They're not triangles. So keep that in mind, but all of them would be considered faces. So both the bases and the lateral faces together would be considered just the faces. We also have what are known as edges. Edges are where 2 faces or a face and a base meet. So for example, let's look at this cube. Our edges would be these different pieces right here, because as you can see, they connect those 2 faces together, or a face and a base together. So the edges would be the edge parts of these different shapes. And then we also have vertices. Vertices are where the edges meet. So for example, our vertices would be right here, these points where they connect. So these are what we know as vertices. Okay, does anyone have any questions about faces, edges, or vertices? No? Okay. Now we're going to look at pyramids. Okay, a pyramid is a three-dimensional solid whose base is a polygon. The pyramid sides are triangles that meet at the top. So a little bit different from prisms, actually a lot bit different. Our base is still going to be a polygon, so this would be the base. Well, its sides are going to be triangles. So these different sides are triangles, and that's what makes a pyramid. So our sides are triangles, and then our bases will be that polygon. Okay, if the polygon were deleted before they were translated and stacked, it would create similar polygons that would eventually reach a point. So basically what this is saying, if you think about, basically, how can I do it? If you think about a square, okay, say we have a square. If you continue to stack that polygon on top of each other continuously, and you're changing the sides, so it's a deletion, it's shrinking, right? As you continue to stack that square on top of each other, what it will actually create is this pyramid that we see right here. And so that is how a pyramid is formed. It's basically stacking these polygons, but instead of stacking these polygons and keeping the size, you're actually shrinking the size as you move upward. And so that's how we get a pyramid. Once again, pyramids are named by the shape of their base. So here our base is a square. This would be our base. And so this would be a square pyramid. Here our base is a triangle. So this would be a triangular pyramid. Here our base is a pentagon. So this would be a pentagonal pyramid. And here our base is a hexagon. So this would be a hexagonal pyramid. So very similar to prisms, the name comes from whatever the base is. Okay, any questions about pyramids? Questions, concerns? Okay, now let's look at some vocabulary. Faces, we already saw. Faces include both the base and the lateral parts of the pyramid. So for example, here we have a base. So that's one face. We have two faces, three faces, four faces, and five. So that would have five faces. So basically you want to count the base and you also want to count the lateral part. So that part that's surrounding that polygon, all of those things would be faces. We also have edges. Again, edges are where the segments where the lateral faces meet. So where our faces meet are edges. So for example, I'm trying to draw it as perfect. This would be an edge. This would be an edge. So where those different faces meet is our edges. In this one, we have what is known as an apex. An apex is the top point of the pyramid. So this top point where those triangle pieces meet, that is known as our apex. So that is something new. And then lastly, the height of the pyramid is a segment connecting the center of the base to the apex of the pyramid. So our height, whenever we're asked to find the height of the pyramid, what we're going to look at is the distance from that apex to the center point of that base. And so that would account for the whole height of that pyramid. Okay, any questions? Okay, so now we're going to go ahead and look at cross sections. So basically a cross section is an intersection of a plane and a three-dimensional figure. So basically say you have a three-dimensional figure and you take something and cut right through it. That would represent the cross section. And so ideally what the cross section, what we're looking for is what shape does our cross section give us if we were to cut just a very, very thin slice out of that three-dimensional figure. And so that's a cross section. The cross sections are parallel to the bases, so they create the same shape as the bases. So that's something to keep in mind. Your cross sections, basically when you're cutting directly in the middle of these different three-dimensional figures, your cross section is going to give you the same shape as the base. And so here the base is a square. And so therefore our cross section would also give us a square. Here our base is a triangle. And so that being said, we can conclude that our cross-section, that very thin slice that's going to come out of a cross-section, is going to be a triangle. And that happens when our cross-sections are parallel to the base. So if we're cutting parallel to that base, that's how we get the cross-section to be the same as the base. Okay, so let's look at cross-sections of pyramids. So we have two different types of cross-sections that we can have. We can have a horizontal cross-section, which will be parallel to the base, and then we can have a vertical cross-section, which will not be parallel to the base, that will actually be perpendicular to the base. So only when a cross-section is parallel to the base do we get the exact same shape of the base as our cross-section. If it is parallel, we're going to get a completely different type of shape. And so here we actually have the same type of pyramid. They're both square pyramids, but one is a horizontal cross-section and one is a vertical cross-section. So if a pyramid is sitting on its base, then a horizontal cross-section will produce two-dimensional figure that is the deletion of the base. So basically, if the base here is a square, and because it's a horizontal cross-section, which means it's parallel to the base, that tells us that our cross-section will also be a square. Okay, here again, we have the same figure, but what's happening is we're taking a vertical cross-section. It says a vertical cross-section of a pyramid through the apex will produce a two-dimensional triangle. Why is that? Well, because we are not cutting parallel to the base, and so because of that, we're actually cutting parallel to these lateral faces. And so even though this base is a square, this cross-section will follow what the lateral faces are, and so this cross-section will actually be a triangle, which is the shape of our lateral faces. These are triangles. Okay, so a little bit different depending on what type of cross-section you have. If you have a vertical cross-section, your cross-section is going to match that of the lateral face. If you have a horizontal cross-section, your cross-section is going to match that of the base. Okay? It says the triangles will have a base length equal to the width of the base of the figure, and the height is equal to the height of the pyramid. So if I'm cutting directly down that apex, the triangle that I get is going to have the same width as the base and the same height of the pyramid. So that's what it's saying. A vertical cross-section not passing through the apex of the pyramid with the rectangular base will be trapezoidal. So if it doesn't cut the square pyramid directly down the middle, then we'll get a completely different shape. We'll get a trapezoidal. Okay. We'll get a trapezoidal shape if it does not cut it directly down. Okay, can you put this next to the door, please? Thank you. Thank you. Okay, so this one says, keep in mind the orientation of the figure when thinking about the cross-section. These are both triangular prisms with a vertical cross-section. So depending on how the figure is placed, here it's placed on its base and here it's placed on its lateral face. Depending on that, the type of vertical cross-section you get can be different. And so here you get a rectangle, and here you get a triangle. And it's all dependent on how your figure is facing or how it's sitting. And so this one's sitting on its base. These are the bases. And this is sitting on its lateral face. Okay. Next thing we are going to look at, so that was cross sections. Next thing we're going to look at is how do we get cylinders and cones. So by rotating two-dimensional figures to create three-dimensional solids. So what if a two-dimensional figure is rotated about a fixed line? If a square or rectangle is rotated about a line that intersects the rectangle, a cylinder is formed. The dimensions of the cylinder will depend on the rectangle's dimensions, along with where the axis of rotation with respect to the rectangle was. The top and bottom of the rectangles create circular bases as it is rotated. So basically, if I were to go ahead and take a piece of paper and I were to rotate it about one of the edges, what it would create is a cone. So that's what we see here. And you can see here, this triangle is basically getting rotated about this edge right here. And as it does so, it creates what is known as a cone. So rotating a rectangle around creates a cone. So, a cylinder, sorry, this is a cylinder. A cylinder is a three-dimensional solid with two parallel lines and congruent circular bases. So here we have that three-dimensional solid, and all the bases will be congruent. So if this base has a radius of 5, then this base will also have a radius of 5. And so those two bases will be congruent to each other. Same thing, this one has a radius of 3. This one will also have a radius of 3. So rotating anything other than a square or rectangle will not produce a right cylinder. And so to produce a cylinder, we want to rotate either a square or a rectangle. Now it will produce a cylinder. Now, how do we create a cone? Well, solids can be created by rotating right triangles and isosceles triangles about a vertical and horizontal line that intersects the triangle being rotated. So if I took this triangle and I were to rotate it around, what it would create is my cone. And it can rotate about any point. So I can rotate it about this point, I can rotate it about this point, or I can rotate it about this point. Whenever I rotate a triangle, it's going to create a cone. So whenever I rotate a square or rectangle, it's going to create a cylinder. Whenever I rotate a triangle, it's going to create a cone. A cone is a three-dimensional solid with a circular base and one apex. So the base will always be circular of a cone. And these two also have apexes, kind of like the pyramids that we saw. Okay, the base of the cone is a circle. The height of the cone is the segment connecting the center of the circular base and the apex, kind of like we saw with the pyramid. The height would be from the center point of the base to the apex. So here would be height, and here would be height as well. Okay, and then cones do not have any edges or vertices. Obviously, they do not have edges because none of the faces kind of rotate around each other. They don't meet at a certain point, so they don't have edges, and they don't have vertices because they don't have points at which our faces connect. We do have an apex, which we might confuse for a vertex, but it is an apex, so it's not a vertex. Okay. So what do the cross sections of cylinders look like? So if a cylinder is sitting on its circular base, then the horizontal cross section will be a circle that is congruent to the base of the cylinder. So here we have our base that's a circle. If it is in fact a horizontal cross section like we saw before, the base will be equal to whatever the base is. And so our cross section here is again a circle. If it were a vertical cross section, however, then the polygon created will be a square or a rectangle. And so basically if we were to cut through the top and the bottom perpendicularly, so we're meeting the base perpendicularly, then what it creates is a cross section that is a square or a rectangle, which is different because here our base is still a circle, but our cross section is going to be either a square or a rectangle depending on the type or what was used to create the cylinder. Okay, so very similar to the other cross section we looked at. If it is a horizontal cross section, then our cross section is going to be equal to whatever our bases are. If it is a vertical cross section, they are not the same, and it really just depends on what type of shape you have. The cross section will change if the cylinder is not on the circular base. So if it wasn't sitting on its bases, then obviously the cross section would be a little different, kind of like we saw in the other figures. Cross sections of cones. A horizontal section of a cone is sitting on its base is a circle that is smaller than the base. So if my base here is a circle, which it is in fact, if it is a horizontal cross section, then my cross section will also be a circle, but because it's a cone, it will be a smaller circle. So we'll also have the same figure. They're both circles, but one would be smaller than the other. The cross section would always be smaller. And the reason that is because if you think about it, the way we form a cone is we can stack a bunch of circles on top of each other. And so depending on what cross section you take, that circle is going to be a little bit smaller. Vertical cross sections, again, on the other hand, are not going to be dependent on what base we have. Here we have a base, which is a circle. Sorry about that. Where am I? Here we have a base, which is a circle. If it is a vertical cross section, the vertical cross section passes through the apex of a cone. We'll have a triangle whose base has the same length as the diameter, and of the base of the cone, its height equals the height of the cone. So basically, if we have a vertical cross section and that cone is sitting on its base, which is the circle, our cross section in this instance would be a triangle. And so again, you can see that if it's a vertical cross section, your cross section is not going to match the figure or the shape of your base. And lastly, we have a sphere. A sphere is a set of all points in a space, a given distance from a fixed point. So very similar to the circle. A circle is basically created by its center point is equal distance from all of its outer points. Same thing with a sphere. So that's what a sphere is. Whenever a plane intersects a sphere, so whenever we have a cross section, the cross section is called the great circle, as it is the greatest circular cross section that can be taken from the sphere. The great circle has the same radius and diameter as the sphere. A great circle divides a sphere into two equal halves. Taking a cross section at any other place along the sphere also results in a circle, but the radius will be smaller. So if we have a cross section that is directly in the middle of a sphere, it will create what is known as the great circle. If, however, we have a cross section at any other point, for example, if I had a cross section right here, that circle which is produced out of that cross section will be smaller, a little bit smaller. So keep that in mind. But every single cross section of a circle, whether it's horizontal or vertical, will always be a circle. Okay, so two-dimensional figures can create three-dimensional solids, which we looked at today. We looked at prisms, pyramids, cylinders, cones, and we also looked at spheres. Okay, so we also looked at spheres. We looked at the vertical and horizontal cross sections of these solids, which will form two-dimensional figures. Remember that if we have a horizontal cross section, specifically of a figure that sits at its base, then its cross section will be equal to or the same figure as its base. If we have a vertical cross section, then it is really just dependent on what type of figure you have. So the cross section will likely not be congruent to that base. Unless it is a sphere, then for a sphere, it doesn't matter if it's a horizontal or a vertical cross section, you're always going to get a circle. Okay. Any questions about anything we've gone over today? Okay. We'll go over some practice problems tomorrow, but if there's no other questions, you guys may log off, and I will see you guys tomorrow. Bye, guys.